Hello, this is Mr. Huber. In this lesson, we're going to explore exponential growth and decay. An exponential function is one that is written in the form we see here, y equals ab to the x. A and b would be some numbers, a not equal to 0. And if you put a 0 in here for a, 0 times anything that bx would become 0. So if a was 0, this should be y equals 0. Okay? And b needs to be a positive number other than 1. Okay? So again, if it was 1, 1 to the first power, second power, third power, fourth power would always be a 1, so it wouldn't change anything. So we're going to see an example of an exponential function here, y equals 2 times 3 to the x. The a value would be 2, the b value would be 3, and then to the x. The x would be some inputs. We're going to plug in numbers for x. -2, -1, 0, 1, and 2 we see in this table of values here. When we plug those values in, these are the y values that we will get out of the function. Keep in mind, when you plug a -2 in here for x, okay, when we plug a -2 in here for x, 3 to the negative second means 1 over 3 to the second. Remember, a negative exponent means we write it as a reciprocal, so it'd be 1 over 3 squared, which is 9. Then we have 2 times 1 over 9. That's how you get the 2/9. So be aware of how we're going to work with those negative exponents when we plug negative values in for x. And when you plug a 0 in for x, anything to the 0 power is equal to 1. So 3 to the 0 power is equal to 1 times 2. So what you're going to notice here is that the y-intercept, when you put an x value of 0 into an exponential function, you're always going to get the a value for your y-intercept. Because any number, whatever b is, to the 0 power is going to be 1. 1 times a is just a. So when you plug a 0 in for x, you will always get the y-intercept. The y-intercept of an exponential function will always be the a value. So that's something important to keep in mind as you're going and working with these and graphing them and things like that. The other piece of this to look out is the b value. Okay, that's what we're multiplying the y value by each time it goes up. Think about it again this way. If we have 3 to the first, that's 3 times itself 1 times. If we have 3 to the second, that's 3 times itself twice. 3 to the third is 3 times itself 3 times. We keep multiplying 3 by itself one more time. We're multiplying by 3 another time every time that x value goes up by 1. Okay, so that's what the b value comes through in these equations. So the a value is the y-intercept. The b value is what that amount is you're multiplying the y values by each time to get the next y value. So now we're going to mostly look at what this means in terms of graphs. If we're going to graph this equation, a thing we can do is make a table of values. Like we saw in those other examples where there are tables of values written, we can make a table of values for x's and y's. Okay? And we're going to put in -2, -1, 0, 1, and 2 as our x values. When you plug a -2 into this equation, you're going to get 3 to the negative second. That's 1 over 3 to the second. That's 1 over 9. When you plug a -1 in there, it's 3 to the negative first. Negative first, which is 1 over 3 to the positive first. You put a 0 in there, and you're going to get 1. You're going to plug a 1 in there, you get 3 to the first, which is just 3. And you plug a 2 in there, you get 3 squared, which is 9. So those are some values that we could now plot on our graph and draw the graph through them. You may be wondering about the a value. Okay, the a value, there's nothing in front of the 3 to the x is a 1. This is 1 times 3 to the x. The a value is the y-intercept. Again, x value of 0, you get the a value, y-intercept of 1. So this has an a value of 1, a b value of 3. If you look through here, multiply by 3, you get 1/3. Multiply by 3, you get 1. Multiply by 3, you get 3. Multiply by 3, you get 9. Okay. So now we can plot these points on our graph. And -2 and 1 over 9 is going to be really close to 0. -1 and 1/3, right there. 0, 1, right there. 1, 3, and then 2, 9. And now we could draw a graph through these points, and it's going to be a smooth curve. We don't connect them with rigid lines to each point. It's going to be a smooth curve, and it's going to level out. It is never going to reach 0. This graph will never have a value of 0. I don't care what you plug in for x. 3 to any number is going to be something. It's never going to be 0. So this graph will keep coming closer and closer and closer to 0, but it will never actually reach 0. All right, and then on this end, it'll just go up and keep rising forever as you keep putting in higher and higher values for x. So you can make a table of values and be able to plot those points to see what the graph looks like. Exponential graphs are going to look like that smooth curve we just saw there in that last example. pretty much every time. Now we have 3 times 4 to the x. So now we have an a value, right? We have an a value of 3, and we have a b value of 4, okay? So when we go to graph this, we can make a table of values, x's and y's, and we're going to plug in -2, -1, 0, 1, and 2 again, and we put a -2 in for y, or in for x. Our y value is going to be 3 times 4 to the -2nd. That's 3 times 1 over 16, 1 over 4 squared. So that's 3 over 16. When we put a -1 in for x, we're going to have 3 times 4 to the -1st, which is 3 over 4 to the 1st, 3 over 4. When we put 0 in, it's 3 times 4 to the 0. That's 3 times 1. And if you plug 0 in as an exponent, anything to the 0 power is equal to 1. 4 to the 0 power is equal to 1. Okay? Then we put a 1 in, we have 3 times 4 to the 1st, which is 3 times 4, so that's 12. And then we plug a 2 in, we have 3 times 4 squared, that's 3 times 16, and that's 48. So we're going to need to adjust our scale on our graph here, because to get 48 in, maybe we're going to count by 5s, let's say. Okay, so I'm going to count by 5s on my axis. This is going to be 5, 10, 20, 30, 40, and 50. So I'll be able to get all those points in on my graph. So when I plug in -2 in for x, I got 3/16 for y, right? When I plug -2 in here, I got 3/16. Really pretty close to 0. So -2 and then 3/16 way down there. Not on 0. It's hard to draw it that close to 0, but you want to be just above the axis. And then we have -1 and 3/4, -1 and 3/4, right around there. 0, 3, right? We're going by 5, so we don't. And then we're going to plug in 1, 12. So 1, 12, right around there. And then 2, 48, and way up here. So again, it's going to be a smooth curve. We can see that it's going to curve down here, and it's going to level off, and we're going to get really close to 0 again. We can see as we start putting in higher x values, that graph just takes off, the y values, increasing rapidly. As you take 4 times itself multiple times, you're going to keep getting higher and higher y values. Okay, so you can see, again, the exponential graph looks very similar to the one we just did. If your graph doesn't look like that basic smooth curve, you're going to have an idea you plugged a pointer wrong. Maybe you messed up with a negative exponent, or you forgot to multiply by the 3 in one case or something. You could screw it up. Make sure you're paying attention to, does my graph basically look like what you're seeing in these last 2 examples? You'll know if you're on the right track or not. All right, a little trivia here about capitals. Okay, where was Michigan's first state capital? Right now it's in Lansing. It wasn't always in Lansing. In fact, the first state capital of Michigan was Detroit. Okay, Detroit was where the center of everything in Michigan was, right by the water, right? As people were traveling and getting to this area by water, that was an easy spot to get to. Even coming up through Ohio, right? You get to Detroit pretty quickly. Why it was moved in 1847, in fact, it was moved to Lansing for 2 main reasons. One, to get the capital more centrally located and to kind of drive things through the rest of the state. So it wasn't all just located in the southeastern part near Detroit. So it was a geographic switch in that region. The reason, because they wanted to push people out away from the Detroit area a little bit and, be able to manage that whole state that was, farther away, so centrally located. And also getting it away from the water was important because there were British troops stationed in Canada just across the river in Windsor. And so they didn't want the capital to be that easy to invade if something happened. So moving it further inland made it more safe and protected, and also made it more centrally located throughout the rest of the state. So a little interesting thing there about your capitals in Michigan. All right, now let's look at some more interesting information about exponential functions. All right, I want you to graph this one again. You should be through this table of values, fill that in, okay? Draw what you think the graph looks like, then press play again, and let's see how you did. All right, so if we're looking at this example now, and hopefully you've tried it yourself, let's put in those values. So first, if we're going to put a -2 in for x, we're going to have -2 times 3 to the -2nd. Okay, that's -2 times 1 over 3 to the second. So it's negative 2 over 9. So we're going to have negative 2/9 for the y value. We put negative 1 in, it's going to be negative 2 times 3 to the negative first. So it's negative 2/3. You put a 0 in for x. 3 to the 0 is 1, so that's negative 2. When you put a 1 in, that's negative 2 times 3, which is negative 6. And when you plug a 2 in, 3 squared is 9, times negative 2 is negative 18. And you'll notice each of these values. When I multiply to get the next one, it's times 3. Negative 2/9 times 3, negative 2/3 times 3, negative 2 times 3, negative 6 times 3. Right? That b value, whatever the b value is what these are getting multiplied by each time. Our a value here should be our y-intercept. It is, so that makes sense. Now we're going to graph this. On our graph here, maybe we want to go by 2s. Okay, so slide this up a little bit so we can see the graph maybe a little better. So we want to graph this going by 2s, okay, on our y-axis. So we're going to go 2, 4, 6. Again, we're going to be graphing some negative y values, but we'll still go by 2s on the negative side. So negative 2 and then negative 2/9, just below 0. Negative 1 and negative 2/3, right around there. And then we've got 0 comma negative 2, 0, negative 2, 1, negative 6, and 2, negative 18. Okay? And so when we graph this curve, it's going to approach 0 still and not cross it. And then we're going to have a smooth curve through our points. And it looks similar to the graph we had before. It's kind of flipped over on the other side of our x-axis, right? This is our x-axis. That's what that negative value for a will do, okay? This negative a value here means you're going to have a graph that looks like this. When they are positive a values, the graphs went like this, okay? It's still that same basic curve. It's just taken from the first and second quadrants here, and it's flipped over the x-axis, so it looks like this in the third and fourth quadrants. Your y-intercept is still the a value. Negative 2 is the a value. It still goes through the y-intercept of negative 2, right? 0 comma negative 2. So same basic premise and functions. A graph looks generally the same with that curve. Just some basic things you want to look for in terms of should your graph be going up as you go to the right, should be going down as you go to the right, based on the a values and looking to make sure it doesn't make sense. Right? Does my graph look like what I'm expecting? Is it going through the right y-intercept? Does it have that basic curve I'm looking for? So you'll know if you maybe made a mistake, especially with making your table of values. All right. Those graphs we were just looking at were exponential growths. Now exponential decay is very similar, except that your b value is going to be between 0 and 1. Okay, the rest of this is all the same as we've seen before, except now, before we had exponential growth, the b value was greater than 1. Now it's going to be between 0 and 1. Okay, not negatives. And it could be a fraction, it could be a decimal, it could be like 1/3, it could be 0.2, something between 0 and 1. All right? And we're going to look at and see what that is for our graphs. You're going to see it doesn't change a whole lot. Okay? But here's an example of exponential decay, because we have a b value of 2/5. Okay? That's between 0 and 1. So we can make a table of values just as we were before. Now we have a fraction to an exponent, so that might change things a little bit. If we plug a negative 2 in for x, we're going to have y equals 3 times 2/5 to the negative second power. Okay? Remember, that means we're going to have a reciprocal. So this is 3 times 5 over 2 squared, positive. Okay? That's going to be 3 over times 25 over 4. That's 75 over 4. Okay? 75 over 4, again, we could turn that into like a decimal. It might be easier to graph that way. It's a little under 20, right? 4 times 20 would be 80. Okay, so you could divide, you get a calculator, you can divide. 4 goes into 7 one times, 35, 4 goes into 35 then, 8 times and 3/4. Or if you put it in the calculator, it's going to be 18.75. That's fine, as long as you know how to graph that. So I'm going to put it as a decimal because probably you're going to end up putting that in your calculator and getting a decimal answer. That's fine. Okay. In fact, you can put in your calculator 3 and then times 2/5 to the negative second. Right, put it in your calculator correctly. You don't have to do all that work by hand, as you're hopefully finding this as you go through on the other problems as well. Know how to put in negative exponents, fractions, and let the calculator do some of the hard work for you. So you put a negative 1 in for x, and you're going to get 3 times 5 over 2, because 2/5 to the negative first is a reciprocal, so that's 15 over 2. Okay, that'd be 7.5. When you put a 0 in for x, 2/5 to the 0 power, I don't care what it is, to the 0 power is 1 times 3. So that's 3. Again, our a value is the y-intercept. And our 3 times 2/5, that's 6/5. Okay, a little more than 1. And then we're going to have 3 times 2/5 squared. Okay, when we put a 2 in for x, that's 3 times 4 over 25, which is 12 over 25. Okay, 12 over 25 is just under a half, right? 12 over 24 would be a half. This is just about a half. Okay, now we want to graph those points. Okay, so when we go to graph these points, slide this up a little bit, make sure we can see our whole graph on there. When we graph these points, we have -2, and I'm going to go by 2's again, so we get up to 20 here on our y-axis because we want to get to 18.75. So -2 and then 18.75 will be right around there. Okay, kind of where the 2 touches there, so it might have blended in a little bit, so it was the point right there. And now we're going to have -1 and 7.5. So that's going to be not quite at 8 here. Okay. Then we're going to have 0, 3. And we're going by 2's, so between 2 and 4. Then we have 1 and 6/5 is a little more than 1. And then we're going to have 2 and then a half, right around there. So when we draw our graph now for exponential decay, we're going to see that it goes from the left to the right, decreasing and approaching 0, but it's never going to reach 0. So it has that same smooth curve. Okay, exponential growth will curve up like this. Exponential decay will curve down like this, approaching that that x-axis. Okay, so it has some of the same features we want to be aware of when we see exponential growth, decay. What do we expect the graph to look like? So we'll know if it kind of does or not, and if we're on the right track. But same basic premise of plugging in values, making a table, and being able to plot those points and graph them. Okay, so let's check out an example here for you to do. So try this one out again. You should be able to see if you're on the right track as we go through it here after you have a chance to pause it and then play again to see how you did. All right, now that we're looking at this exponential, y equals -2 times 1/4 to the x. So if I'm just looking at it, I have an a value of -2, and then I have a b value of 1/4. So this is going to be exponential decay because this is between 0 and 1. All right, so when I plug a -2 in for x, I have -2 times 4 over 1 squared. So that's 4 over 1 is 4, which is 16. So -2 times 16, you should get 32. And you can use a calculator to do these. So we're going to have 32. When I put a -1 in, that's -2 times 4 over 1. So that's -8. Oh, I should have put -32 there. Sorry, I missed my negative sign. All right, we got to check that. -8. I put a 0 in for x. -2 times 1, because 1/4 to the 0 is 1, is -2. And then I put a 1 in for x, so I have -2 times 1/4. Okay, that's -2 over 4, which is -1/2. If I reduce it, and I put a 2 in, that's 1/4 squared is 1 over 16. So I have -2 times 1 over 16. That's -2 over 16. Okay, that's -1/8. -1/8. And if you're wondering about that b value and how it's what you multiply by each time, multiplying by 1/4 same as dividing by 4. So this is like dividing by 4, dividing by 4, divide by 4, divide by 4. Multiply by 1/4, right? That b value is what we multiply by each time. Here's our y-intercept, 0, -2. We could plot these points. In this case, maybe you want to go by 5s or something else. If you go by 2s, you're going to get to 20, depending on if you have a grid drawn or if you're drawing your own graph. Just be consistent, right, in what we're going by on our x or y-axis. It doesn't have to be the same. Our x-axis, we can still go by 1s. And our y-axis here, I'm going to go by 5s. So that'd be 5, 10. Okay, so -2, 32, just a little bit above 30. We have -1, 8, or -8. I put that in the wrong spot. Let's erase that last dot, right? Got to pay attention to those negatives. -2, -32, right around there. -1, -8, so not quite to -10. 0, -2, our y-intercept. 1, -1/2, and then 2, -1/8, and that's almost at 0. And so when we draw this graph, we're going to see what it looks like here is approaches the axis and curves, just like we saw before. Again, our exponential decay function we had in the last problem came down like this. Now with that -2, it's that same graph flipped over, just like we saw before. If this a value is negative, it flips the graph over the x-axis. Exponential decay flips over the x-axis. Okay, when it was exponential growth, and then if we flip that over the x-axis. So we have a basic idea of what the graph should look like. Understand again how those a and b values affect things. Be able to make your table, and you can see some consistency. You're just going to be practicing it and getting used to how do I work with the negative exponents, the fractions, how am I graphing them. And you're going to see, again, a lot of those similarities in all these different equations. So it's practicing, getting used to them, and again, recognizing what is it going to look like ahead of time. Is it growth, decay? Do I have a negative or positive a value? Where should it go through the y-intercept? So you are making sure that it's matching up with what you expect, and if not, giving yourself a chance to go back and see where you can maybe make some adjustments.